charge particle has come. Let's say it has given me this charge. Yeah. So this is what my single charge particle has come. What kind of mode I am coming up? Let's just see. So the mode which I am coming up with is voltage कहाँ लगाएगा भाई? High voltage आप लगाएगा क्या down?
Down.
This is minus, this is plus, right? Oh, I do not want to change it. मैंने आप लोग कहोगे सर इसमें यहाँ पे था, उसमें वहाँ पे था, कुछ गड़बड़ा जाएगा. पर उससे कुछ होता नहीं. Okay, let's just understand this configuration in which instead of our emitter, we have put one resistance. Yeah? Now, this is plus, this is minus, resistance is this one. What will happen, whenever the current will flow across this, whenever current will flow, my resistance will see something like IT times R, which will be the voltage which is developed across here. That's how this thing works. But interestingly, if you look into this structure, immediately you realize this detector acts as a capacitor, having some capacitance which we call as CD, detector capacitance. If I add the capacitance of all the stray elements, what are stray elements? Here we are just talking about wires. Each of the cable having its own capacitance. Then total capacitance is nothing but the detector capacitance plus the capacitance of any cable which is going on. Suddenly I am seeing C and R in parallel because I am going to take my output around this resistance. So we have C parallel to R. Now this C parallel to R, of course you have done the basic course on electronics. Suddenly you will start realizing that this configuration, which is the CR circuit type of configuration, will have its own characteristic time for the decay and rise. Why that would come? So let's just think what is happening. When you are applying voltage, originally, if no particle comes through it, even though the electric field is there, but no charge is deposited on these plates. Why? Because no charge was collected. Since no charge was collected, so anything which you do with Q is equal to CB, which means B is equal to Q over C. What is this V? Voltage developed across this guy is zero. All the voltage appears across the resistance or the capacitance. If no event happening, no charge migrating, what will happen? Voltage will appear across where? High voltage. Capacitance का resistance क्या है भाई? Infinite, which means सारी voltage कहाँ है? To begin with, this across my capacitance. This resistance is of the order of megohm, whereas the resistance of the capacitor is of the order of gigohms, more than that. And hence your voltage initially will drop across the resistance which is of the highest value, across capacitor. Now, if a particle passes through, what will happen? It will create charge. This charge is, remember this thing, IT as the function of T. This guy has given you Q in time EC. Now what is happening when this charge starts getting collected? So there will be the charge starting getting collected. Capacitor will start getting charged up. Yeah. Now depending on the decay time constant, my capacitor can first charge and then discharge, or as soon as my capacitor gets charged, it may get discharged. Yeah. So what is the decay time constant? Let's just set some parameters here of this circuit. दिखेगा टाइम कांस्टेंट RC circuit in parallel. Sir, this is just R type C, nothing else. Now, this tau, which is the ticking time constant, has to be compared against another time in order to figure out whether first my capacitor gets charged and then discharged, or my capacitor doesn't charge much and continues to discharge. What is the other time in this system? So that's the time which is there, collection time. So there is collection time, which is the time during, depending on my detector, it's the time in which charges migrate and get collected into each of the electrodes. So ultimately these two, this time should be compared along. But I will be doing it for one, and I will be giving you a homework for another, which is explained in non-spoke, but I still want you to go through it, and wherever you do not understand, you will ask questions. Make sense? Yeah. So let's just do this for one. What is the one which I am considering? I am considering the one where tau is much greater than Tc. Which means that the decay time constant is far more than the collection time. So if this guy is 10 to the power minus 6 seconds, then this guy will be tau of the order of
-3 or
milliseconds. Yeah, you can make it anything. It has to be greater than this now. If it is 10 to the power minus 9, then correspondingly even 10 to the power minus 6 will be larger. So depending on what the Tc is, let's say just to have some numbers, 10 to the power minus 6. Now I would like to draw the charging of the capacitor. As soon as capacitor starts charging, some voltage will start coming across this. This means this voltage which will start coming here is going to ultimately get discharged through that resistance. Earlier there was nothing to discharge, now there is something to discharge. What is that we are going to discharge is what we are going to see. It's a simple CR circuit in parallel, where C has two terms. So I want you to make this guy again, and beneath this we are going to make that. So please do that. Remove, I actually wrote lots of things here. So now, what am I interested? I am interested in Vt. Ultimately, which will come where? It will come across the resistance. Yeah, that's what I am seeing. Now, this guy has come, up to this point has come. How this Vt will change is what I want you to draw. V across the capacitor is related with Q over C. Q keeps on getting accumulated. As we are saying that the total area under the curve will be the total charge. But total charge did not immediately come up. Initially, this much of the current has flowed. Then this much additional. Then this much additional. So how am I going to see? So how am I going to see? Basically, for each of the time, I should be integrating IT for each small time. How will that curve look like? So from here to here to here, what will this curve look like? This should be the typical of what we say is capacitor charging. This guy will keep on increasing. This guy will keep on increasing, reaches to some max. No, okay, make sure that you understand. What is happening? What have I drawn here? I have drawn V, which is Q by C. C is the capacitance of this detector and this. It's a constant. So it is basically Q getting converted to V. Now, if you integrate over this much time, then the charge is small. Now charge keeps on getting accumulated. So ultimately it gets all the charges accumulated. After this point, no additional charge can accumulate for one pulse. Right? So this point where it is going to have the peak will correspond to what value? Q, which is the entire charge divided by C. So I will call this as
Next.
This is what we call as the capacitor charge. I mean, this is what you have done in your 11th class, by the way. This is what is the capacitor charge. After getting charged to full value, what it will do? This guy starts discharging with the time constant, which is what we call as the RC time constant, or what we call here tau. Now this thing is happening only if tau is much greater than Tc. What's this important thing? During the time Tc, when the capacitor is charging, there is no discharge happening. If I reverse the condition, then as soon as capacitor sees a charge,
It will be discharged.
it will discharge. So make sure you understand that this condition is pretty important. Let's just now understand the basics of this one. There are only two important things. But first, have you understood what is happening here? One is capacitor, which is our detector, is charging. Next, it will discharge through R, and Vt is the voltage which will appear across the RT through all the times. Since they are in parallel, so minus the direct voltage, the pulse will look like this. V0 is a direct voltage supply. It's only a DC supply. Yeah. So I do not need to worry about the DC component. If I worry about this, only thing which is called pulse. What is pulse? Variation of voltage or current with time. For DC, there is no variation with time. For sinusoidal AC, we have the sinusoidal variation with time. For this kind of a process, we have the charging and the discharging. So not the sinusoidal, but the exponential decrease or the rise. Yeah? So if we have understood this, let's just consider the two important parts. First part number one. It is that charging is related with detector only. Why? Charging depends upon the collection type. Collection is happening all inside the detector. There is no effect of the RC. So how good will be the rise time will depend upon how small is my geometry or how fast my electrons are migrating inside. So the charging is, this portion is detector only. Whereas the discharging, I am controlling through
resistance.
External resistance. Because C is the constant. So, in the charging discharging curve of the pulse, we have the charging completely controlled by the detector, discharging completely controlled by the external circuit. Which means I can decide whether it should fall immediately or I can decide if it falls slowly, depending on what value R I am going to take. Remember, the exponential minus t divided by RC will retain its exponential character depending on what the RC values would be. Yeah, it's an important point because we choose R values such that depending on what we want to figure out, we want to immediately decay or we want to decay later. But see one thing which is inherent in this pulse mode. information about the time because my pulse will rise exactly in the time Tc. So the amplitude of the pulse will happen exactly at the Tc, and the entire charge is nothing but this point. Vmax is equal to Q by C, which means that I am not going to lose no information loss of Q or Tc of given event. In this case, we were averaging over many such. So we were not able to figure out what was happening in the individual event. In this case, I am able to see what is the total charge collected in this one. Oh, this is nothing but the amplitude, which is the Vmax, appearing across the resistance. In what time it has risen? Rise time, that is giving you the timing. The timing and total charge or the amplitude information, both information is retained into this one. Yeah, that's pretty interesting. So, this no information loss of this means that the pulse mode of the counting, why I am calling pulse? Because Vt is now changing with time. Earlier my average current was constant, right? Here we do not have any constant current. It's changing with time. Now the next pulse, if it comes here, then you see that my decay time hasn't given you the complete zero. Suddenly, my system is not going back to its original zero voltage. I am not going to resolve that. Either I am going to make my RC decay pretty fast, or otherwise I cannot resolve it. Pulse mode works with lower irradiation rate. Why? Because if the irradiation rate is high, then my RC has to decay pretty fast here. But RC cannot decay faster than the correction time. Otherwise, I won't even see this kind of a pulse. So, why pulse mode works with lower irradiation rate? Because in pulse mode, I need sufficient time to get charged and then discharge. Right? Pulse mode retains the information of the charge and the timing. In pulse mode, the charging portion is completely determined by detector and discharging portion is completely determined by the external circuit. And the final thing which is generally, in terms of the numerical which is asked, is what is the Vmax which is achieved, and that is Q over C. In pulse mode, the charge collected is inferred from the amplitude of the pulse. So Q is completely inferred from the amplitude of the pulse. From now onwards, in the pulse mode, I can interchangeably talk about charge collected or pulse amplitude. So the next thing which we are going to do is to see what happens to this pulse amplitude as we change the high voltage in our system. This is what the 5 regions of our gaseous detector would be. But in today's class, what we wanted to harp on, that there exist 2 modes. One is the current mode, another is the pulse mode. Current mode is of limited use whenever we want the information about the charge collected or the individual pulse information. Pulse mode is quite important when we want that information. Pulse mode can work at lower rates because it has to take care of the entire. However, current mode works with higher irradiation rate. It is averaging over any number. So whatever number is coming, I am averaging over. Yeah.